our warm-up. The function f of xy has the following Taylor polynomial at the point 2, 1, namely 7 minus 3x minus 2 squared plus 6 times x minus 2 times y minus 1 minus 4 times y minus 1 squared. And based on this Taylor polynomial, we're asked which of the following statements is true about the point 2, 1 for f of xy. Maybe it's not a critical point, or maybe it is a critical point, in which case it's a max, min, saddle, or we just don't have enough to make a conclusion. What's the answer? B, huh? B is good. It is a local max. Because we don't see those linear terms, so in other words, we don't see like something times x minus 2, something times y minus 1, that means that the partial derivatives with respect to x and y are 0, so we know it's a critical point. Then we read off the second derivatives, and we're careful. This negative 3 is not fxx, that's half fxx. So it's actually negative 6 is fxx. Similar, negative 8 is fyy. But fxy is indeed 6. Plug it into your discriminant, you get a positive number. That tells you it's either a local max or a local min. And then you look at second derivative test in a slice. Either one is negative, it's a local max. So there we go. Ah, good, good. We can do these. Nice. All right. Well, here's a quote, another dubious, a lot of people say Mark Twain said this. No evidence he did, but he could have. And history doesn't repeat itself, but it often rhymes. And I think that's true in a lot of cases, and especially in mathematics. You know, math doesn't repeat itself, but it's often very similar. So the ideas that we saw in Calc 1 and a little bit in Calc 2 are coming back. And they're like, ah, this feels familiar. We've seen this before. And recognizing things that you've been done before, that you've seen before, it's easier to say, okay, now I know how to incorporate, now I know how to make things work. And this also comes back to the idea of find patterns. Math is about patterns, but so is life. Life is about patterns. And if you're able to find patterns and use them, it'll help you go surprisingly far. All right. Well, today we're talking about absolute max and absolute min. And so we'll just jump right into it. Suppose you want to find absolute max and absolute min on a closed and bounded region. Well, how do you do it? And the answer is there's actually a very simple way to do it, because you have a nice fact. And what's our nice fact? We'll put it over here on the side. We didn't write it down yet. So fact, if we have a continuous function, so continuous here is taking the nice. So continuous function on a closed and bounded region, then the conclusion is the function achieves an absolute max and an absolute min. So if we have a nice function, our domain is nice, then we get to say, there's somewhere where this function takes on a maximum possible value in the domain, and somewhere where it takes on a minimum value in the domain. Now, we do need this notion of closed and bounded. We've mentioned these words before. Bounded just means we don't go arbitrarily far away. So you can put your whole domain into a big circle of some size. Closed says, I'm going to keep my boundary. I want to have all my edges. And why do you need these things? Well, you can take a very simple example. Suppose we have our domain. It's just everything between 0 to 1 for both x and y. So 0 less than or equal to x, less than or equal to 1. 0 less than or equal to y, less than or equal to 1. So there's our domain. And now we'll take a very complicated expression, f of xy equals x plus y. What's the largest value that you can get given that I don't want to include that x goes strictly between 0 and 1 and y goes strictly between 0 and 1. What's the largest you can get? It's a trick question. Yeah, well, someone's using fancy words like limit. They're trying to play with my heart. But you know, my heart only has room for arctangent. So, but we can see, look, if I want to make this expression x plus y big, I should make x big, I should make y big. And it's like, well, I want to get up to the corner. But can I get to the corner? It's the corner in my domain. No. But I can get close. I can get closer and closer. So there's this notion of limit. So the problem is if I don't include the boundary, or even the same issue if I'm not bounded, I may not be able to reach the point where I can achieve my maximum. So it's just this notion of I'm able to actually get to where the maximum occurs. Now, there's a lot of math behind this fact. A lot of math. Usually it's about another 2-3 years beyond our class in terms of like the mathematical background. But we're just going to assume this as a fact. All right. So given that we know it exists, it makes our job a lot easier. And I like to think of this as we channel our inner Santa Claus. So this is an attempt of a drawing of a Santa Claus. And what do we do? We're going to make a list. We're making a list and we'll check it twice. We're going to find out which points are nice. So, how do we make a list? Well, we just say, given that I know it exists, I only have to look at the points where it could happen. So, you say, well, maybe it's on the inside. So I could have a region. Let's say our region is a triangle. So I could have a region that looks like this. And I say, well, it might be that the critical point happens on the inside. So how do we find that? Well, you set the gradient to 0. So similar as what we talked about finding critical points. And here, this just ignores this notion of, are you closed bound? It just says, don't worry about your region. Just set the gradient equal to 0 and solve. Now, once you solve, those points may or may not make the list. Now you're like, wow, why might they not make the list? Well, the thing you don't need to check is don't bother with classifying. That's too much energy and it's a waste of time. What you do need to check is where the point is. Say the point I found is here. Would that make my list? Yes, because that's in my domain. What if the point I found was over here? No, because it's out of my domain. So I only keep the ones that are in the interior. Things which are out of the interior, they're just out. They don't make the cut. Okay, so you found the critical points that could be on the inside. Now you have the boundary. So you find the critical points on the boundary. And how do you do that? Well, you turn the problem from a two-dimensional problem to a one-dimensional problem and say, let's use one-dimensional tools. So we reduce our function down to one variable. How do we do it? Well, there's a couple of ways. The easiest way is to think about how can I parameterize the curve. There's other ways that do that as well, and we'll talk about that. One piece of advice, always make sure you get the corners. So if you have a triangle, always include the corners. If you have a rectangle, always include the 4 corners, and so forth and so on. So you've made a list. And essentially what the list is, these are all the points where the absolute max and absolute min could occur. Now, you plug those points into the function. And you get a bunch of numbers out. And finally, you look at those numbers and you say, okay, what's the biggest number? Whatever the biggest number is, that is your absolute max. And whatever your smallest number is, that is your absolute min. All right, that's it. That's the whole procedure. There's no like, oh, we have to run through some test. No test. Just make a list of everywhere where it could happen, plug it in, and look for the largest and smallest numbers on your list. All right. Do you see the idea, the flow? Okay. Shall we do an example? We're going to either way. All right. So, first problem. Find the global max and global min for the function g of xy is x squared minus 4x plus 2y squared minus 4y plus 1 over the triangle with vertices 0, 0, 3, 0, 3, 3. All right, so let's first get a handle on what this looks like. It looks like a triangle. Now you might say, how did you know that so quickly? Because it said it. I'm very sneaky. I like to read problems before I do them. It's a pro tip. Read the problems before you try to solve them. All right. So we have 0, 0, 3, 0. That says x equals 3, y equals 0. Okay, so that's over here. And 3, 3. So that's up here. So I'll draw the triangle. And it doesn't say it very well, but it's meant to be a triangle where we include the insides. Okay, so here's our region. It will be closed and bounded. And by the way, on these problems, you will sometimes see the word absolute max and absolute min, or you'll see the word global max, global min. Those mean the same thing. And so if you ever see absolute max or absolute min or global max or global min, you're like, I'm making a list. I already know what I'm doing. I'm making a list. All right. Well, our procedure. What was the first thing we were going to look for our list? Yeah, gradient equals 0, the inside. All right, so we're going to have our list over here. So, gradient equals 0. That's the same thing as saying fx. Oh, sorry, not f. It's g. G. Okay, gx. Gx is 2x minus 4. Set that equal to 0. Gy. 4y minus 4. Set that equal to 0. Now we have 2 equations and 2 unknowns. And so we stare at this for a few minutes, hoping that we can figure out the solution. What would be the point x comma y that satisfies 2x minus 4 equals 0 and simultaneously 4y minus 4 equals 0? Yeah, 2, 1. Okay. They were nice. Okay, do we include that on our list? Well, let's see. 2, 1. Let's see, where would that be? We can be a little bit more precise here. That would fall here. Does that make the cut? Yes. All right, we have something for our list. Woohoo! Our list has grown. Okay, so that takes care of any interior points. Now we get to the boundary points. All right. So, for me, I always like to throw in the corners right away just because it makes me feel like I'm making progress. And then I also don't forget to do that. So let's add the corners. So the corners, 0, 0, 3, 0, and 3, 3. So corners always make the list. Okay, all right. How many sides do we have? 3 sides. So we're going to get to do this 3 times. We have our bottom side, our right side, and our slanty side. So bottom, right, slanted. Which one do you want to do first? Bottom, okay. People were like, oh, I want to do slanted. They're like, I want to do the hard one. Okay, so the bottom. What characterizes this bottom curve? Or maybe, can you describe this bottom curve like as a formula? Yeah, y equals 0. So what happens is on the bottom, our function changes. So we're going to replace y by 0. So it becomes a function only of one variable, in this case x. X squared minus 4x plus 1. So now I've reduced it to a single variable. That's what we mean by reducing it. So you can use your old Calc 1 tools. So if we were doing optimization using our old Calc 1 tools, what would come next? Take a derivative. What's the derivative of x squared minus 4x plus 1? 2x minus 4. And then we set that to 0. What does that give us for x? Gives us x equals 2. And remember, we're on the curve y equals 0. So this is the bottom y equals 0. So that really gives us the point 2 comma 0. So, and I should have said, does that make the list? And it does. Because that's where 2 comma 0 is. All right. What side do you want to do next? Choose the right. Okay, so on the right side, what characterizes the right side? X equals 3. So for the right, x equals 3. So we're going to replace x by 3. So g of 3 comma y. Well, let's just do the x equals 3 part first. So that would be 3 squared is 9. 4 times 3 is 12. And a plus 1. So that's 10 minus 12 is negative 2. So it's negative 2 plus 2y squared minus 4y. So it becomes a single variable function. Now it's a function of y. It doesn't really matter what it is. The point is it's one variable. So we use one variable tools. Take the derivative. What's the derivative become? 4y minus 4. Set that to 0. And what does that tell us? Y equals 1, which is the point? 3 comma 1. Does that make the cut? Yes. 3 comma 1 is on our list. And I guess I should have marked where the corners were since they're also on our list. The list can grow quite a lot. These problems take time. All right. One more side and we'll be done. So our final side, the slanted side. Now, what describes this side? Y equals x. You can describe it by a curve, y equals x. Okay. So y equals x. So what we can do is we can replace y by x. So we can think of it as g of x comma x. the goal to get it down to one variable. Well, so if I have x comma x, I see I have an x squared and a 2x squared. That makes 3x squared. A minus 4x and a minus 4x. That makes minus 8x and a plus 1. So I'm putting in y becomes x, and then just saying what does this become as a function of the single variable x. Take a derivative. What do we get? 6x minus 8 equals 0. So what is x? 4/3. Giving us the point. 4/3, 4/3. Does that make our list? Yes. So roughly here. Okay. So we've made a list. It's not a bad idea to check it twice. Did you get everything? Did you get the interior? Did you get the corners? Did we get all of the sides? Now it might be, by the way, sometimes there's nothing on the side other than the corners. So, but you don't know. Sometimes there might not be anything in the interior. A priori you don't know, but you have to check. Do we have all the points? Have we looked everywhere where the absolute maximum could occur? Yeah, so this is our list. Okay, so we finished our make a list. Once we have a list, what happens next? Yeah, we plug it in. We plug all of them into the function. And some of these are easier to plug in than others. 0, 0 is usually pretty easy. 0, 0, 0, 0, 1. Okay, that was nice. And, yep. Okay. Which ones do you want to do next? 2, 1. Okay, so for 2, 1, let's see, we'll do some scratch work downstairs. 2, 1, we get 4 minus 4. Oh, that's nice. 2. 4 minus 8. Okay, all right, all right. Fine, make me be correct. Plus 2 minus 4 plus 1. All right. 4's cancel. Those 4's cancel. See, some 4's cancel. That's good. Minus 8 plus 2 plus 1. Negative 5. Okay, 3 comma 0. Now, where do you plug it in? It turns out you have options. You could plug 3 comma 0 into here. You could also plug it into here. You could also plug it into here. If you plug g of 3 comma 0, what would you do for this part? You put y equals 0, you get negative 2. Okay, how about g of 3 comma 3? You could come here, plug in y equals 3. You could come here, put x equals 3. You could come here and put x equals 3, y equals 3. They'll all be the same answer. It seems about the same amount of work. Let's suppose we do it here. So g of 3 comma 3, negative 2. 2 times 9 is 18. 4 times 3 is 12. So you have 18 minus 14. That gives you a 4. How about 2 comma 0? Well, we can do it here. We get 4 minus 8 plus 1. 5 minus 8, negative 3. 3 comma 1. You can come here. That's negative 2. So y equals 1 plus 2 minus 4. Giving us Negative 4. Okay, and g of 4/3, 4/3? Yep. All right. We get 3 times 4/3 squared, that's 16 over 9, minus 8 times 4/3, that's 32/3, and plus 1, that's 3/3. Now 3 does go into 9, so it's 16/3 minus 32/3 plus 3/3, so that's 19 subtract 32. 19 subtract 32 leaves us with negative 13 over 3, which is negative 4.3333 for engineers. Okay, so there's our list. We found our list. We plugged in our points. What comes next? Do we look at the numbers? What's the biggest number on our list? 4. What's the smallest number? Negative 5. That beats negative 4.33333. So, our final answer, we have our global max is 4, and it happens at 3,3. Sometimes they'll ask you where it happens, sometimes they don't, but it's not hard to add that. And the global min is negative 5, and that happens at 2,1. And there we go. Now, if you look at this problem, it looks very, there's a lot of stuff here. This is scary. But if you break it down, it's only mildly scary.
To get full credit on that test, so we have to show the value of all the points, or can we use some intuition and just see like what we think are going to be the best? And then,
To get full credit on a test, I think they would want you to put all the points in.
Okay. Like, if
Yeah.
if you're not finding all the points is the best, like we have to show the value for all of them, because if we know that some of them aren't going to be the biggest.
Yep, we want to see that work. And you might say, this seems like a terrible one. This is on the shorter side of these problems. So I will say the longer side we don't ask. All right, any questions? Yes?
Is it going to tell us to include the inside of the triangle, or how did you know to include points inside rather than?
Well, I kind of knew this when I was asking for it. But sometimes it'll be very explicit. It'll say inside the triangle. So for instance, it might be a problem that says, give the absolute min and absolute max for a function on or inside the triangle with vertices 0, 0, 0, 4, and 4, 4. So that might be how it phrases the problem. Oh, hey, there's another problem here. Wow. But you know, I feel like I haven't given you guys enough chances. So I feel like you should do this problem. But this one, there's a lot of intermediate steps. So maybe let's talk about some intermediate steps and we'll just check in. What's a good first intermediate step? Okay, so let's make that your first intermediate step. Take a minute. Draw the region. All right, can anyone tell us what the region looks like?
Triangle.
Good, it looks like a triangle. Exactly. I knew you guys were going to nail that part. Let me ask you about the three sides of the triangle. What are the functions for the three sides of the triangle? So someone said x equals 0, y equals 4, and y equals x. All right. So there's our region. Good. Okay, so once you know your region, what's a what's a good next step to take? Okay, set the gradient, find it in the interior. Okay, so that's your next step. Set the gradient equals 0, solve. Okay, do we have a place where the gradient equals 0?
1, 2.
Gradient of f equals 0. That leads to the point 1, 2. Is that going to make our list? 1, 2 is roughly here. Okay, so now you've done the interior. What comes next? Boundaries. Okay, throw in the corners. Put the corners on. All right, has anybody figured out the corners yet? No, still working on the corners? Okay. Give you another 30 seconds for those corners. Those are tricky corners. Okay, so what are the corners that we're going to add to our list?
0, 0, 0, 4, 4, 4.
0, 0, 0, 4, 4, 4. Where do they come from? They told us. Oh, they were nice people. They could have tried to make it like, oh, very mysterious, like here are these 3 curves, and then, no, they just said, here are the corners. Okay, so you have 3 sides. Should we do them one by one, or just let you work on them? I'll let you work on the three sides. Take a couple minutes. All right, do we have some boundary points we can add onto our lists? Did anybody do the slanted side, y equals x? So on y equals x, what does the function become? So y equals x, it becomes 2x squared minus x squared minus 4x plus x, also known as x squared. And that's a pretty easy function to solve. 0, 0. It's already made our list. We don't need to add it a second time. For x equals 0, did anything make the list? Sorry, what? 0, 2. Well, that would be this point. That's new. For y equals 4, does anything make the list? Someone mentioned 1, 4, which is up here. And that makes the list. So just to be clear, you have the functions x squared for y equals x. For y equals 4, it becomes 2x squared minus 4x. For x equals 0, it becomes minus y squared plus 4y. And you take the respective derivatives and set them equal to 0. Okay. Are those all the points? Yeah? What's next? Plug them in. Okay, so what numbers do we get? 2, 0, 0, 16, 4, negative 2. Largest? Okay, here's our max. Smallest? And there's our min. Okay. Yay! So this was from a final exam from a few years ago. So it's like, yeah. Sorry, what? Actually, yes. I like this problem. I didn't write it. I'm kind of jealous of the person who wrote it. This is a nice problem. So, all right. Good. We have a few minutes left. So we'll do a speed run through the last problem. Because I always like a good challenge. Global max and global min for the function 2x cubed plus 3y squared minus 12x, where x squared plus y squared is less than or equal to 4. What's our region look like? It's not a triangle. It's a circle of radius 2. Okay. Cool. Now you might say, where are the corners? We'll get to those. There will be corners, but we'll talk about that. All right, so we start with the inside. So our inside says take the gradient of h, set it to 0. That says we want h sub x, which is 6x squared minus 12 equals 0. H sub y, which is 6y equals 0. Well, okay, that tells us y equals 0. Here, we can add 12 divided by 6. X squared equals 2. So this leads to two possibilities. X is plus minus square root of 2. So we now have two places on our list. Plus the square root of 2, comma 0, minus square root of 2, comma 0. And square root of 2 is smaller than 2. So these 2 points there. All right. Cool. Progress. So that's the interior. Now, where do we go next? Got to do the boundary, right? Add in the corners. Well, yeah, about that. We'll get to that in a second. So what's our problem? We want to reduce it so that on the boundary, we have one variable. But on the boundary, we have x squared plus y squared equals 4. Now, this doesn't seem like it's very conducive to that. But what can we do? Well, we say, look, there's only one place where y shows up. And it shows up as a y squared. And on the boundary, what's true about y squared? So on the boundary, h of xy becomes 2x cubed plus 3 times 4 minus x squared minus 12x. So that's 2x cubed minus 3x squared minus 12x plus 12. So we can take a derivative with respect to x because we got it down to one variable. So that would give us 6x squared minus 6x minus 12 equals 0. And you can pull a 6 out, x squared minus x minus 2 equals 0. And, they were nice. This factors as x minus 2, x plus 1 equals 0. So that gives us two places, x equals 2 or x equals negative 1. Now, if x equals 2 and x squared plus y squared equals 4, what is y? Y has to be 0. If x equals minus 1, and that's this point. If x equals minus 1 and x squared plus y squared equals 4, what does that say about y? So y squared has to be 3, so y is plus or minus root 3. So you get these points. Minus 1, positive root 3, minus 1, negative root 3. Okay. Have we made a complete list? Is this everything? And why not? There's one more point to add to our list. What point is missing? Not the center. That would be from the interior. And the interior we rolled out. We've already gotten all the points in the interior. It's a good guess. The center is a good guess. Well, they're all the farthest point. That's the thing about a circle. They're all equally far. Where's your corner at? Here. Why do you have to include that? And that's our last thing we'll stop with. But why do you have to include negative 2, 0? Because this is your function here. However, is this for all values of x? No, because you only are going from x between negative 2 to positive 2. So this is, you're doing a optimization on the interval from -2 to +2. So you have to include your endpoints. So you do have a boundary condition. That's your corner. So anyways, from here you would plug in, you'd find your largest, and then you'd have the answer for absolute max. All right, we'll stop here. Pick up again next time.